On behalf of Postgraduate Department of Chemistry and IQSC Nabira Mahavidyalaya Katol, welcome you all on the fourth day of the 10 days lecture series on 132nd birth anniversary of late Shibikula Nabiraji. On this fourth day of lecture series, we are privileged to have the eminent speaker, Dr. Bhushan Popatkar, and sir is going to deliver a talk on IR spectroscopy in connection with characteristic vibrational frequencies of functional groups, and the second one is the introduction to Scifinder and class. Welcome, sir. Now to welcome our today's guest speaker, I would like to request Dr. Nilesh Gandhare, convener and assistant professor, Nabira Mahavidyalaya Katol, to introduce our speaker, Dr. Bhushan Popatkar, sir. Over to you, sir. Dr. Gandhare, sir.
Thank you, ma'am. Good afternoon, one and all. It is my great pleasure to introduce Dr. Bhushan Popatkar, sir, for today's session of 10 days national level lecture series. He is assistant professor, Department of Chemistry, University of Mumbai, Kalina, Santa Cruz, Mumbai. He received his PhD in organic chemistry from Mumbai University. He has deep understanding of green chemistry and extensive experience of teaching and research. He has many national and international research publications and one book to his credit. He has delivered many invited talks and presented his work in national and international journals. Dear participants, please join me welcoming Dr. Bhushan Popatkar, sir, who is going to talk to us about two topics, that is IR spectroscopy and introduction to Scifinder and CAS. Doctor?
Yeah, am I audible, sir?
Yes, sir, yes.
Yes, first of all, I would like to say thank you very much for the kind introduction from Gandhare sir, who is very senior to us, and we can say is our path makers actually. Thank you again, sir. And without talking here and there, I'll just start with the presentation. Just confirm whether the screen is visible or not. Then I can start with the topic which is assigned to me actually. Okay, is it visible?
Yes, sir. Screen is visible, sir.
Okay, fine. So here there are two different topics that I have choose for this particular 10 days seminar. So here topic one is IR spectroscopy, where we will talk only on the characteristic vibrational frequencies of some functional group. Means the intention, my intention to take this topic for you people, those who are working in the research area of organic chemistry, or those who are pursuing their masters in chemistry, specifically in organic chemistry. At the end of this topic, or 1 hour discussion with IR spectroscopy in connection with characteristic vibrational frequency, you will get to know that interpretation of IR spectrum. So once you will receive IR spectrum of any known or unknown molecule, you will be able to analyze the peak, that which peak is responsible for what particular thing, and the meaning of that particular peak, why that much so intense, why it is medium, why it is weak and all. So first of all, once you understood the basic phenomenon regarding the IR spectroscopy, in that case principle of IR, and then the characteristic vibrational frequency, and at the end, as I said, that you will be able to interpret the IR spectrum. And the second topic which on time I have taken is that introduction to Scifinder, which is chemical abstract services. So what is meant by Scifinder, how it is too important amongst the researcher, and at the same time how this database is maintained by Columbia Ohio Institute, that we'll get to know after we'll have a discussion on the Scifinder. The Scifinder is nothing but the chemical abstract services. Besides Scifinder, you are also having other sources also like Reaxis and all. And when we will talk about this particular thing, that time I will talk about the others also. So let us start with the first topic, that is IR spectroscopy in connection with the characteristic vibrational frequencies of some of the functional group. Here I have not take the all functional groups, but the important functional group which are coming in the regular studies of your MSc class, that only I will try to explain. Now let us start with the talk. These are the some content as I have told you earlier, characteristic vibrational frequencies of some of the functional group. Which functional group? That we have I have mentioned over here alkane, alkene, alkyne, aromatic hydrocarbons or aromatic compound, you say alcohol, ethers, phenol, amines, and lastly the carbonyl compounds, where you can find here carbonyl compounds. There are aldehydes, ketones, esters, amides, acids, and anhydrides. So each functional group on the IR spectrum, you will have a peculiar peak. That peak arises from the given functional group, and how it is looks and how we can interpret that, whether it is hydrogen bonded, whether it is free from the hydrogen bond, whether it is CHNH, whatever the functional group, that we can find on the IR spectrum. But before to understand that characteristic vibrational frequency, we must know about the principle of IR. So before to start with the principle of IR, we should know what is IR. We know that this is a kind of radiation or electromagnetic spectrum which have a small portion, like I have highlighted here is an infrared radiation region. So here this IR region is very long, very broad. You see here it is ranges from 12,800 to 10 centimeter inverse. This is the long range, I can say. Okay, so when we come towards the IR, or towards the IR means from X-ray, UV, visible, to here microwave and radio waves here. Okay, so you will have, first of all, again here you can see gamma rays, X-ray, UV, visible, and here you are having IR. So whenever we are coming from gamma to IR, so it is near IR, just started the position of IR. So it is from 12,800 to 4,000. This is near IR range. Then this particular IR region, as I have said, is divided into 3 different regions for the convenience of our studies, because each region is applicable to different applications. Because you see far IR is applicable for another application, mid IR is applicable for some of the organic compound analysis, and near IR for the another you can say application. But here, as I said, it is long range, and we need to do the analysis of organic compound in the particular fingerprint region. Means most of the organic compounds, they vibrate or they show the characteristic vibrational frequency in the mid region area only. They will not show any observation in far IR or near IR. That's the reason mid IR region is very famous among the organic chemists, not far or not near. So for this convenient of a study, as I have said, we have categorized, or the broad range we have categorized into 3: near IR, mid IR, and far IR. So here 12,800 to 4,000 is a near IR. This 4,000 to 200 is a mid IR region, which I have already said is very much famous among the organic chemists. And then far IR, which is again 200 to 10. But this 400 to 200, in that the most used IR region is this one, 400 to 670. Means that you can find all the characteristic vibrational frequencies of the functional group in here. Means all the organic compounds, the characteristic absorption you can find in this particular region only. So this region is most used region of the IR range, you can say. Now this technique and applicable, which is based on the IR region, which is there in the IR region. Now these are the normal modes of vibration, but before to understand the normal modes of vibration, we first needs to understand what is meant by the basic principle of IR. Now here I think it is visible, right? Principle of IR, is it visible, sir?
Yes, sir. Yes, sir.
Yeah.
Only
So
the heading is visible now.
Yeah, heading is visible. Principle of IR spectroscope. I have intentionally kept this area blank to start with the explanation for the principle of IR spectroscopy. Now, when we say IR spectrum, and just now we have seen that this IR region is a part of electromagnetic radiations. Means that you will have a particular Christian pro. Okay, so this is the wave, which is the electromagnetic radiation. Now, for a time being, you imagine this is nothing but the IR radiation. Now, when we say any electromagnetic radiation, we are having the magnetic and electric field associated with it. Yes or no? Yes, of course, we are having electric and magnetic field associated with it. Okay, so you can say this is the electric field upper, and this is just a 90-degree perpendicular is a magnetic field, and this is characteristics of what? IR radiation or any electromagnetic radiation you see. This electric field possesses electric charge amongst it. Okay, so the charge is distributed among what? The electric field of your radiation. Now, any molecule which possesses dipole moment is called as IR active molecule. Means the molecule needs to be IR active. The most important thing is that that molecule should possess dipole moment. If that molecule does not exist with the dipole moment, that will not show IR spectrum. This is a very much clear idea. Why? The reason you will get to know later. Now here you see, for a time being, you imagine carbon dioxide, a very much famous molecule. Some of the vibrations of carbon dioxides are IR active, some of them are inactive. Why these are active, why these are inactive, that also you will get to know when you will have some correlation with Raman spectroscopy, but that is not our case. For example, you are having carbon dioxide here. Some of the vibrations, like earlier, you can see a symmetric, asymmetric, in plane, out of plane, rocking, scissoring, wagging, twisting. That are the basic thing that everyone knows. That will come later. But first of all, you see here, this carbon dioxide possesses dipole moment. Now, what is meant by dipole moment? Dipole moment is nothing but the charge separation. When you will have charge separation in the molecule, that molecule must have the electronegativity difference. Then and then only that will have charge separation, otherwise not. Now here, in specific case of carbon dioxide, you can find there is a charge separation because you are having carbon as a delta positive and oxygen you will have delta negative. So of course, you can find here there is a charge distribution among this carbon and oxygen unequal. This is anisotropic. So here, when we are having this carbon and oxygen and there is charge separation, and of course this electric domain, okay, and this positive domain. But before this, each and every molecule, it's not carbon dioxide, any molecule you say which possesses dipole moment, they have their own vibrational frequency, okay, called as natural vibrational frequency. Or the molecule, they vibrate at room temperature also with their natural vibrational frequency, means their own vibrational frequency. Okay, so there are certain vibrations like you can have in carbon dioxide also, symmetric, asymmetric, bendings and all. So this, without interaction with the IR radiation, initially it vibrate as per their natural vibrational frequency. Like it can have asymmetric, symmetric and bending vibration also. Now, when we fall this particular radiation, I said earlier, this negative portion means electric field of this IR radiation, when interacted with the negatively charged or dipole, in short you say dipole, when dipole of this particular carbon dioxide, then there is the matching during natural vibrational frequency of this carbon monoxide or any molecule interacts with the IR radiation, specifically the electric field of the IR radiation, then there is a matching between the natural vibrational frequency or some of the vibrations of this carbon dioxide and IR radiation. Then resonance will take place, and molecule, once they receive exact energy which is required for the excitation, when it is received from this IR radiation, then this molecule goes to the higher excited state within a vibrational level. Now, what is meant by within a vibrational level? So to understand this thing, we need to learn first of all the total energy of the system, as we know that E0 to E infinite. E infinite. What is electronic energy to electronic infinite energy? So here in between electronic energy levels, you can find E0 to E infinite. That means that E1, E2, E3 and so on. So infinite. But when I select this E0 to E1 here, if I selected E0 to E1 here, E0 to E1 here, then I can have many vibrations here, vibrational lines here from nu 0 to nu infinite. So what you can say, total energy of the system, which is E0 to E infinite, from E0 to E1, you can have many vibrational lines. Okay, so nu 0, nu 1, nu 2, nu 3, nu 4 and nu infinite means electronic energy levels embedded with n number of vibrational level, and we select only nu 0 to nu 1. From here to here, nu 0 to nu 1, you are having again infinite rotational lines. Okay, rotational, this is generally denoted by J0 to J infinite, rotational energy levels, J infinite. Okay, so here we are concerned about the vibrational levels. So as I said, this molecule when goes to excited from ground state, when absorb the exact amount of energy from the IR radiation after resonance, this goes to the excited state within the vibrational level. Now within a vibrational level means it will not cross any electronic excitation because that energy is not sufficient to carry out the electronic excitation. And therefore, when it goes to this nu0 to nu1, nu0 to nu2, or nu0 to nu3, why? Because they are closely associates, nu0, nu1, nu2, nu3. So nu0, nu1, nu2, and nu3. And because of this, we know that Boltzmann distribution law when says that maximum species should have at the ground state. So here basically you are having all the molecules at ground state, but as nu0 and nu1, this seems to be very much close with each other. There are certain chances of out of this 100%, 1% of the molecule can also stay at excited state. It should not, but it exists. The reason behind it is that they are very much closely associates with each other. The distance between these two is very small. And that's the reason that molecule when absorb the energy out of 90, some of the 80% molecule you can say goes to the first excited state, that transition called as the nu0 to nu1 transition. Similarly, nu0 to nu2, some of the molecules can also go when they absorb the more energy, nu2, and some of the molecule also can goes to the nu3. So nu3 from nu0 to nu3. And because of this excitation, you will have different bands in IR spectrum. Nu0 to nu1 results a fundamental band in spectrum. Fundamental. Nu0 to nu2, this is first overtone. This is second overtone. And beside this, you can also have one extra band in the IR spectrum. That is because of the excitation. As I said, 1% molecule can exist here in nu1 that can also get excited to nu1 to nu2. And because of the nu1 to nu2 in IR spectrum, you will have hot bands. The confirmation of hot band can be done by doing the temperature at the experiment at high temperature, because at high temperature the concentration at nu1 will increases and the intensity of this hot band is also increases, so that you can confirm that the given peak in the IR spectrum is because of the hot band, or it may be a different band. So when you carry out the experiment at high temperature, the intensity of that particular bond which was thinking that it is because of the hot band get increases because the concentration increases at nu1 at high temperature. Anyway, so here, as I said, the principle in short, how will you keep in mind here? IR spectroscopy means IR radiation possesses magnetic and magnetic field and electric field. Electric field carry out with the electric field, electric field and magnetic field, of course. And then you will have here a molecule which possesses dipole moment, and that particular or any molecule which possesses dipole moment, they can vibrate along with their natural vibrational frequency. And when this natural vibrational or fluctuating dipole, this is a very specific word you can keep in mind, that fluctuating dipole. This fluctuating dipole when interact with the IR radiation, specifically the electric component of the radiation, then the molecule goes to the excited state within their vibrational level, these vibrational levels. And once it is goes to the vibrational levels, that will arise as fundamental, first overtone, second overtone, and hot band. And now, as I have said, this molecule can vibrate, but there are specific terminologies that we can use here. Asymmetric vibrations, we know that here you can see these are the vibrations, stretching vibrations and bending vibrations. These are the two important vibrations that can observe in IR spectroscopy. So stretching vibrations, again, asymmetric stretching and symmetric stretching, that many times people learn this topic in the BSc classes, so no need to spend too much time, but you know better that stretching, again, symmetric and asymmetric. Bending, that bending is two type, in plane bending and out of plane bending. Then in plane, rocking and scissoring, and out of plane, wagging and twisting. So this is the background what the IR spectroscopy actually tells us. Now, each molecule, organic molecule, as I have said, have the dipole moment. Most of the organic compound, they are having dipole moment, charge separation, and they also vibrate. even at room temperature. Okay, and once it is vibrating, we can take the advantage so that we are having some fingerprinting. Fingerprinting is nothing but what, at least some of the area where we can identify the given molecules, stretching, bending, vibrations can occur in that particular region. Now before proceeding to the group frequencies, I will tell you that as we know that just now I told you that 670 to 4000 is a range of IR radiation in centimeter inverse, which is a mid-range IR, or simply you can say this is a most used region of IR spectroscopy as far as organic molecules are concerned. Now, when we are having that long area, so there are many molecules, many vibrations, many functional groups are also there. So to avoid the chaos of the fingerprinting region of the different functional group, again this region I have categorized into different 4 regions. Okay, so the first region is from 4000 to 2500. This I called as a XH region. Okay, so what is meant by XH region? XH means heteroatom along with hydrogen. So hydrocarbon is a heteroatom and hydrogen is common. Nitrogen is heteroatom, hydrogen is common. Sulfur is heteroatom, hydrogen is common. Nitrogen is heteroatom and hydrogen is common. So anyway, any functional group you see, any functional group, and which possesses NH, SH, CH, or even SiH also, SiS, silicon and hydrogen. So even OH is a very famous OH. These all functional, or you can say the OH, NH, CH and SH. These are absorbed in this particular region, that is from 4000 to 2500. So it is very much clear that amongst all the functional group, at least we know that heteroatom and H region, that XH region, which is ranges from 4000 to 2500, means you can take alcohol, silicon containing compound, amines, thiols, carbon and hydrogen. Almost all the compounds possesses carbon and hydrogen, hydrocarbons. But here also, when I say CH is aromatic type and aliphatic type. On the basis of IR, you can also discriminate whether the given compound belongs to aliphatic group or aromatic group. That also you will get to know in short. Even NH, that NH is very much important. Amines, whether the primary amine is there, secondary amine is there, tertiary amine is there. By using this IR spectrum and looking to the region of 4200 and their peculiar pattern, you will get to know the given amines is primary, secondary or tertiary. So that we will talk detail about this. This is just a background that I am giving because this background is very much important. If somebody says that this compound have NH, whether it is primary, secondary or tertiary, to find it out. So don't look here and there, just look amongst this particular region. No, just look the region which ranges from 4000 to 2500. So there you will have certain peaks, and looking to the peak design, or you can say the pattern, you will get to know whether primary, secondary or tertiary amine it is there. Okay, now second region is there, 2500 to 2000. 2500 to 2000. This region I called as a triple bond region. Okay, so this is triple bond region. So any molecule which is triple bonded, C triple bond C, C triple bond N, any triple bonded compound, they absorb over here between 2500 to 2000. So whenever you are having olefinic acetylene type of substances or nitrile type of substances, you can find the range that from 2500 to 2000. Okay, now the most important region of the IR is specifically confuse a lot, that is from 2000 to 1500, and that is called as a double bond region. Is all in centimeter inverse. Okay, so double bond region. Why I said this is confusing? Because almost all carbonyls, acids, amides and hydrides, you can take esters and whatnot, amides including, acid chloride, all they have carbonyl absorption over here in this particular range. So how to get discrimination between the carbonyl of aldehyde, carbonyl of ketone, carbonyl of acid, carbonyl of anhydride? So that idea we will get to know by looking this region, not only this region, but we need to take the advantage of this structure, like where we are having aldehyde, COH, and ketone, suppose C double bond O. So both carbonyl, they are having the difference hardly of 20 centimeter inverse of absorption. There you can get confused, but the advantage of this hydrogen you can take, where that hydrogen is not associated with whatever this ketone. And of course somebody can say this is CH3, this is CH3, they are also hydrogen. Then how will confirm that particular hydrogen is of aldehyde, or that particular hydrogen or CH absorption is because of ketone? Because we know that aliphatic range is very much fixed and aldehydic hydrogen range is fixed. So by looking to that range of hydrogen, you can confirm whether that is aldehyde or that is ketone. Okay, that you will get to know in incoming lecture. And last region is, I call this one as either fingerprinting region or single bond region, which ranges from 1500 to 670 centimeter inverse. And here most of the time you can find this single bond stretching, that asymmetric stretching vibrations, and all the bending vibrations occur in the range of 1500 to 670. Even most of the real IR spectrum, if you see, they have up to 500 centimeter inverse. Anyway, you can use from 4000 to 500 or even to 200. That is not an issue for us. But these four regions are very much important to understand the characteristic vibrational frequency. Now, whenever you will have carbonyl, which region you will see? You will see the region that is ranges from 2000 to 1500. Whenever you are having the peak at 2500 to 2000, you can confirm, you can say confidently that it is a triple bond region. So that is because of the either triple bond, the triple bond of C triple bond C or C triple bond N. And that is also very interesting, how we can identify whether that particular bond belongs to what, triple bond C triple bond C or C triple bond N. We know again charge sorry, what you can say, charge separation or dipole moment. You can see C triple bond C, charge separation is less, therefore weak. Three terminology again used in IR spectroscopy: weak, medium intense, and highly intense or intense. Okay, so always C triple bond C existed as a weak peak in the range of 2500 to 2000. Medium means this is small weak peak. Medium means somewhat medium, and intense means it will be very sharp and long. So here weak, medium, and intense, or in other way strong, moderate, weak. Any word you can use, but these are the convention which I have read in many of the books: weak, medium, intense. Even you can use strong, moderate, and weak. Doesn't matter. Now here you see, yes. So like at the end, you can say that the whether that particular molecule holds NH, OH, SH, or CH and all. So each and everything, because this is the characteristic vibrational frequencies where that particular molecule absorb in the particular region. That regions I have given. If you really understood this particular portion, it will be very much easy to understand the other portion. Now here, I just ask all of you, you people really understood this thing, or there is a kind of repetition is needed? You please ask me so that I can go ahead. If not, then I can spend some of the time here only, because this is the most important thing as far as the characteristic vibrational frequency are concerned. Yes? Am I audible?
Yes, sir, you're audible.
Yeah, ma'am. I wanted to ask the same question to the students. If suppose anyone have any difficulty in understanding, they can ask the question so that clarity will be there in incoming topic.
Yeah, they can drop the question in the chat box. If you have any question regarding this particular topic, you can drop the question in the chat box, please. All the audience participants.
Here important understanding is required. Otherwise, whatever we learn in next, that will be again, that confusion will carry forward. We kindly repeat briefly, sir. Yes. So here briefly means what you can see. These 4 lines what I have mentioned here, you please keep in mind. What 4 lines? 4000 to 2500 is a XH region. When I say XH means CH, NH, OH or SiH, whatever. XH मतलब हेटेरोएटम चाहिए उसके पास हाइड्रोजन. 2500 to 2000, it's a triple bond region where all the triple bonded will absorb over there in that particular region. From 2000 to 1500, all the double bonds like carbon-carbon double bond, all benzene, C double bond C you can find. And then carbonyl, because carbonyl is like the C double bond O. So all double bonded compounds, they absorb here in this particular range. And when I say single bond, all single bonds, C single bond O, C single bond N, C single bond H. Now you can ask me the question, NH also. You can ask the question that CH to either base, NH to either base, then how? And you can see this is a different, that is stretching. And what CH, NH you will have here only appears as a bending vibration. Where? In the single bond region. That is the basic difference that you keep in mind. Okay. Except NH, because it not contain hydrogen. So a stretching vibration again coming here in the single bond region. Okay, students. What Charushila? Single bond range in IR spectroscopy, sir, please tell me. Single bond range is this 1500 to 670 or 500. This is a single bond range. Okay. So XH region is this range. Triple bond range is 2000 to 2500. Double bond range is 1500 to 2000. Okay. Or 2000 to 1500, whatever you take. And 1500 to 500 or 670, whatever you take, that will be single bond range. Okay. Okay. Yes. So I will move next. I think the computer got stuck. Just a wait. Okay, fine. Yes. So I hope that this is vanished now. This is finished. I think everyone understood. Now again, there is a time to repetition, those who could not. Okay. So here you will get again better understanding what I have explained there. This is again repeated here. For better understanding, the whole mid-IR region again subdivided into following region. The XH region, as I have said earlier. Then you are having a triple bond region, then double bond region. Then single bond region you are having in the range of 1500 to 500. As I have said earlier, the XH region, which is ranges from 4000 to 2500, where OH, CH, NH, SH, all absorption bands are occurs. Okay, then how will you discriminate between OH, CH, NH and SH? You see, OH band produce broad in the range of 3700 to 3600. Now you see, whenever any OH is there, that OH possibility of occurrence, that particular peak in this particular range. Now this was a range, but for OH, this is a range 3700 to 3600. And believe me, this is not exact range. It is ranges either from 3000 even 450 here 3700. So that much long range you are having for the OH. Now why is it that long range? Because you see, most of the organic compound, whenever possesses OH, they may associate with hydrogen bonding. They may have intramolecular hydrogen bonding, they may with intermolecular hydrogen bonding, or they sometime not possesses an hydrogen bonding. When that possibility of hydrogen bonding formation is not there, when you are having the solvent which is non-polar. In most of the polar solvents, OH groups makes hydrogen bonds, but in non-polar, there is a possibility of that molecule may get scattered. They may have not that chances of formation of hydrogen bonding, but that must have the concentration less than 0.01 molar. When you are taking non-polar solvent and the concentration of non-polar solvent is less than 0.01, then there is a less possibility of formation of hydrogen bonding. Then you will get only in that case sharp peak, provided that non-polar or organic solvent should not have their fingerprints in IR, means they should not absorb the IR radiation. Then your OH will be free from hydrogen bonding. Otherwise, most of the time you will get such a broad peak in case of IR. This is because of the hydrogen bonding. Now, as I have said, hydrogen bonding is intra and inter. There are many examples, ortho and para. We know that ortho, you can say salicylic acid. Ortho and para. Ortho have intra and para have, yes, inter. So they are also discriminated using this IR spectroscopy. This is the actual application of IR spectroscopy, that inter and intramolecular hydrogen bonding can be found out by using their peak, nature of the peak and absorption frequency. Now NH, when I say NH, there are the two type of NH you can find in organic compound, either NH2 primary amine, this is NH secondary amine. Of course, this should be associated with some the kind of substance R. This is 2R, and here you can say the secondary, and in tertiary you don't have any NH vibrations. You don't have any NH vibration. So what you are having here, 2 NH2. So 2 peak, just like W shape. But one is small and one is large, or like this, whatever. So if one is for one nitrogen NH and another one is for another NH, because whenever you are having NH, no, you will get to know in future. Here you see nitrogen, here you are having, here hydrogen you are having, and here hydrogen you are having, and this is R, suppose this is primary amine. Now we know vibrations, one is coming or going toward the nitrogen, and one is coming away from the nitrogen. Another way it is going away from the nitrogen, this is coming to this. So bond length is decreases or increases, and one time when resonance takes place, one of the hydrogen they have good interaction, one of the hydrogen is not, and therefore one is intense and another one is less. So such type of peak, whenever you will find in this region of 3400 to 3300, and nature of this kind of peak is like this W shape. ये W ऐसा होता है, but it is just like this. Okay, so that will be medium intense, because the polar or charge separation between nitrogen and hydrogen is quite good. And then medium intense peak, likewise you will have in the range of 3400 to 3000, and that one can confirm the primary amine. But in the same region you will be only with single such kind of peak, medium intense, only you will not have this W shape, only a single sharp peak. Then only you can say this is because of NH, because there is no other hydrogen, only one hydrogen, this is replaced with R, this hydrogen coming toward nitrogen and going away from the nitrogen, just like this vibration, and you will have simple sharp medium peak. You confirm secondary amine. Now come to the CH function. This is very much important. Again, you see here it ranges, as I have given the range 3000. You imagine below 3000, here you are having 2870 or 50, you see. So in between below 3000 to 2850, any CH vibration you observe, that is because of the aliphatic only. And if there is a CH which is their aromatic, it goes beyond 3000. So this 3000 is a borderline which only suggests us whether the CH is aromatic or aliphatic. More than 3000, aromatic CH, and aromatic CH only 100 centimeter inverse. Okay, so 3000 to lower than 3000 CH aliphatic, more than 3000 and 3100 less than, then you can guess aromatic. So this is the range actually, 3100 to 2850. So here 3000 is a borderline, more than 3000 CH, that aromatic, less than 3000 is called as aliphatic CH stretching. So I hope that you can understand this thing. Now here The same thing they have mentioned, I think. So CH bond aliphatic and aromatic. So again, here you see 815, 3102 this. So I hope that you could understand the NH, OH, CH and SH stretching. SH is also here is the same, but the charge separation is not too good, so weak. And based on the intensity of the peak, we can only determine the given function is of SH or NH. Then triple bond region. As I have said earlier, carbon-carbon triple bond, carbon triple bond nitrogen. So carbon-carbon triple bond, when you are having, it is range, I said earlier, 2500 to 2000, and it is observed in between 2300 to 2050. Same way, CN is there, which also occur 2300 to 2200. Now here some kind of merging of ranges takes place over here. Now how one can find it out? Of course, again we can look to the intensity of that peak. Now, as I have said, C triple bond C, here charge separation is not good. Of course, induced dipole moment is there, but charge separation is not too much good, and therefore you will have very small, weak peak, very weak peak in that particular region. Even such kind of peak are also observed here in case of C triple bond C in the region of this. But the same region, if CN is there, then moderate intense peak you can observe for CN. Okay, so this is the only differentiating criteria for this. Even sometime this is some at your level, no need to keep in mind XH atom, SiO or SiP, that are also just a wait. Okay. So how busy lecture सुरला दे सांगा काय? माझे करेक्शन कधीचे झालेले आहेत. तुम्ही मला मार्कशीट पाठवा, मी तुम्हाला पाठवतो. ठीक. मार्कशीट पण सर पाठवली नाही मिळाली मला, प्लीज ठीक आहे सर. Sorry for the interruption. Now you see here, as I have said, exchange of some massive atoms like silicon or phosphorus, which usually occurs in this range. So this is, you can say, just exceptions. If you go in detail of this, that will take many time, because again it is related with whatever the weight of that particular atom. Sometimes we call it as a mass, reduced mass. Then again that Hooke's law comes into the picture. That will be the physical aspect of your IR spectroscopy. I'm not going too much detail on this. Anyway, so here again the double bond stretching region. This region is very much important, as I have said, because this is most of the time covers carbonyl group. Now the principal bands in 2000 to 1500 is due to the carbon-carbon double bond and carbon-carbon oxygen double bond. So here all carbonyls, again they are showing their absorption in this particular region. This is very much important. All carbonyls, they are going to get going to get absorbed in between 1850 to 1650 centimeter inverse in this region. And we know that carbon and oxygen, the charge separation is very high. Like the most electronegative element in the periodic table after fluorine is oxygen. Okay, so this oxygen will pull the electron from the carbon, making delta positive, and this become delta negative, and charge separation is quite good. And whenever you find charge separation is quite good, IR radiations, they are interacted very easily and very comfortably with this carbonyl. Excitation will take and very sharp peak. I'm telling you, the most intense peak in any IR spectrum results because of the carbonyl or carbon oxygen kind of bond only. Because if except if suppose you are having hydrogen and fluorine kind of substances, then that time the hydrogen and fluorine, because we know that fluorine is more electronegative than oxygen, in that case only you will have most intense because of that fluorine. But here in general, in common way, you can say carbonyl are the more intense peak in the IR spectrum of any. Now this is again exception. Metal carbonyls observe 2000 centimeter inverse above. Of course, in inorganic chemistry, this metal carbonyls, which again I said like MCO, you see this is again triple bonded region, so about 2000 centimeter inverse. So here that metal will have its own effect and all, that is inorganic chemistry, that is far away. Now here you see of course the double bond region, most of the time we need to focus only on carbon-carbon double bond and carbon-carbon oxygen. Now here again I said this C double bond C, it is because of the ethylene you see, or you can also have the benzene also have C double bond C, C double bond C, C double bond C, alternate C double bond C. That means that you are also having C double bond C, all the peaks over here in the particular range. Okay, so here this range is very much important as far as carbonyl and carbon-carbon double bond is concerned. Now come to the last, which is also called as a fingerprint region or single bond region. Now here, all the single bond, as I said, it's not like, rather I can say it's a confusing region. Why? Many peaks are there over here, and that is because of the all bending vibrations. Sometime we need to focus only on some of the important peaks like 691, 627, like peculiar peaks of some of the bending vibrations, specifically rocking and wagging that occur over here in that region of 691 or 721 likewise. But here we need not to bother about this. This fingerprint region is a supportive information that we can get what we are predicting sidewise. So this 1500 to 650, or sometime only you write down 500 centimeter inward. This is a fingerprint region or single bond region, where most of the time you can find C single bond C, C single bond N, and don't like you say C single bond H. H is another region that we have mentioned over there as a XH region. And now, and all the bending vibrations basically occurs in the single bond region. So I hope you could understood the basic regions, and these regions are very much important. Again, a brief: XH region, which ranges from 4000 to 2500, 2500 to 2000 triple bond region, 2000 to 1500 double bond region, and from 1500 to 500 is a single bond region. Now let us start with some functional groups. Okay, now as far as these functional groups are concerned, now you see here aliphatic hydrocarbons we are having. Hydrocarbons means all the compound which is made up from the carbon and hydrogen, where you are having aliphatic hydrocarbons and aromatic hydrocarbons. Aromatic hydrocarbons, we know that benzene or benzenoids, where you are having all Huckel rule follow and all that comes under the category of what is aromatic hydrocarbon. Now hydrocarbon, when I say aliphatic type, which contains alkene, alkene, alkynes and cycloalkanes. So all the alkanes or anything you say where you are having either CC bond or CH bond, not more than that. Can you find another vibrations over here? No possibility, because these are the hydrocarbon. And whenever we say saturated hydrocarbon, then you are having C single bond C or C single bond H. So any molecule you take, and one thing you need to keep in mind always, we are not here for the structural elucidation. You see, if you are having IR spectrum and you are justifying the given compound is like this, then no one will going to believe on you, because we are not under the structural elucidation. But yes, we can say this is the functional group that must be exist in that given molecule. Okay, so this is very much important. Don't go for the structural elucidation. Just try to find out which functional group is there. So whenever I find the peak in the CC and CH, I can say only these peaks are observed in the IR spectrum, then I can say it is only hydrocarbon. Now, which hydrocarbon? That I can't say, because it is not a structural elucidation. That may be hydrocarbon only, but which? No. And that's the reason we only say the functional group. And of course, it verifies. Highly aliphatic hydrocarbon means here again alkene, C double bond C. So of course, alkene and alkene I can differentiate. In one case, I will get C single bond C. In another case, here C H allylic hydrogen. In triple bond C, I can see here this in triple bond region, this is in double bond region, this is in single bond region. CH is aliphatic. When I can say CH is aliphatic, you can get the peak at 3000 to 2850. This is double bond CH, then allylic. So effect of this one again you will have in the range of what 2800 to 3000, but we need to take the advantage of this double bond region. Means in one case you will have less than 1500 peak, here 1500 to 2000 peak, and here you will have 2000 to 2500 peak. On that basis only we can discriminate between the alkene, alkyne and alkanes. Similarly, in case of aromatic hydrocarbon, of course, aromatic hydrocarbon, to discriminate amongst this all rest of the others is again very simple, because aromatic hydrocarbon CH is observed at more than 3000 to 3100 in between, and all of these are again 3000 to 2850. So this is very much great advantage for us to discriminate between the aromatic hydrocarbon. And beside this, you will have double bonds for aromatic hydrocarbons, means the double bond range you will have certain peak. And how to get confirmation, more confirmation for aromatics? Now here in case of aromatic, much more complications will be arises in the region what I have mentioned earlier, that is 1500 to 2000 in between, because this is double bond region. And now beside this C double bond C, you may have many peaks, that is because of the combinational and overtone bands. Okay, so combinational differences, overtone bands, so complexity arises in that range. That means that it is because of the aromatic. Whereas in case of aliphatic hydrocarbon, there will be no such kind of too much complexity arises in aromatic. Now, when we come to the oxygen containing compounds, alcohol, phenols, ether, they can also get discriminate. Alcohol, phenols, ether will come later. Then amines also, same thing we have repeated. Earlier I told you primary, secondary, tertiary, all amines can be differentiated. Then again carbonyl compounds, all carbonyl groups as per their structural things or structural skeleton, we can discriminate between the carbonyl of aldehyde, ketone, ester, amide acid or anhydride and all. Now come to the hydrocarbon. Here you see, this is hydrocarbons. All these hydrocarbons are there. When you say methyl group and methylene group, most of the hydrocarbon possesses methyl group or methylene group. At the end, methyl group, and in between methylene group. Now these methyl and methylene group, they have its own vibrations. Likewise, ये out of plane भी जा सकता है, because here this is not looking planar, because third bond is associated with something and it is rigid, so it may be out of plane. But this methylene completely planar. Here we are having substituent, so CH. It can show scissor, it can show scissoring, bending, all bending vibration like twisting, then wagging, rocking. But here some of the limitations. Now, how we can differentiate then? So this is the chart which I have mentioned here already. You can see the CH asymmetric stretching for methyl. So for methyl, CH symmetric. Symmetric means either all hydrogen coming to the carbon, or at the same time all hydrogen going away from the carbon. So that is symmetric stretching. For methylene is observed at 2960, which is always less than 3000. As I have said, and where that particular peak if appear in that range, you can say this is because of the methyl CH. This is CH of all methyl, or three seems to be very much equal, identical. Now CH of asymmetric type of methylene, methylene ka asymmetric, what means, what does it mean? One is coming here, one is coming out, one is coming in, one is coming out. This is asymmetric stretching, and this appears at 2930. You see, difference is very low, but we will be happy to find out the difference and all. Now again, this was a symmetric stretching of CH methyl. Now this is asymmetric stretching of methyl. Asymmetric stretching means either two are coming near hydrogen, one hydrogen is coming away. At the same time, one hydrogen is going inside and two hydrogen going away. That is asymmetric vibration, which occur at 2870. Same thing you can find for methylene also. Now it is asymmetric stretching. If suppose if it is asymmetric, that must be a symmetric stretching, which appear at 2850. And come to the bending vibration. Methyl show all possible bending vibrations. All bending vibration means scissoring, twisting. This is all what they talk about, and no need to bother about this, no need to keep the values in mind. Just the thing is that, as I have said, all bending vibrations, you see, wagging in methylene, all ranges in, I said earlier or not, in the single bond region, all region here, bending vibration, all this bending, these are coming in single bond region or not? Yes, these are always less than what, 1500, and many peaks you can find there. No need to interpret each and every peak, as I said earlier, that will mislead your understanding of infrared spectrum. Now coming to alkenes. In case of alkene, what you are having, as I have said, CH band, and it is double bonded, so of course it will go here in the range of 3000 to 3100, because here double bond is there. C double bond C, of course double bond region, but not coming interfering in the carbonyl group. Carbonyl group, as I have said, 1850 to 1650. This is the carbonyl. So here it is not showing any peak. Then CH plane bending, CH out of plane bending, forget about this, no need to go. Bending vibrations, we are not giving too much importance for bending vibration, because that will again unnecessarily makes us confusion, and forcefully we need to keep in mind that we don't want. A simple thing, just you keep in mind. Now again here also alkyne, triple bond C, this triple bond CH function, you will have in the range of 3300 to 3215, which is almost NH region. But NH, how to identify with respect to this triple bond CH? Now you only should be telling confident that NH is if NH2 doublet, likewise W shape. Then if it is NH, only its sharp line, medium sharp. But if triple bond CH is there, that is very weak. And this is the basis on which we can discriminate whether it is because of the olefinic, alkynic or not. And the C triple bond C stretching that will appear in the triple bond region. Of course, we know C triple bond C here in, but that will again very weak. Just now we have seen bending, as I have said, no need. Then you see here, as far as octane is concerned, in octane, all possible vibration earlier what we have seen here, no, all these you can find except some of them. Now for methyl, you can say 2971, 2863, these two peaks along with this also there, but our intention to say that it is always less than 3000. So such type of peak you will have for the CH stretching. Then scissoring, methyl rocking, methyl wagging long chain. If you are okay with the understanding, or you can keep in mind, that is okay. Otherwise, what I said here, only you find CH or CC. Okay, so CC here you will have at 728 CC, and here you can find CH. These are aliphatic. Similarly, here I think alkene. Okay, and this is alkyne. So here alkene means double bond region. Yes, this is the double bond region. You see weak, I said no, weak. This is the double bond region, weak 2000. Now this is again triple bond, more than 2000 you can find, and of course less than. I don't know which is exact example of this, but that also contained along with double bond one CH also. That is the reason you can find more than what, 3000 or less than 3000. More than 3000 means because of this C triple bond C. 2000 3000, just now we have seen, no, this you see 3300 to 250. So here you can find, okay, these are the peaks. Sorry, double bond, yes, 3100, 3000, this is double bond, sorry, double bond 3000 to 3100 and all. So these peaks are responsible because of this CH of double bonds. Okay, double bond CH, and this is for acetylene, you see. So for acetylene, you see acetylene, CH triple stretching here, as I have said, it is not too much intense W shape. It should not. It should be very much weak. Okay, it should be very much weak. Likewise, but they have shown intense. Okay, but it should be less intense. And of course, we can find out very easily when we compare nitrogen containing compounds. Okay, now aromatic hydrocarbon, as you all know, this is benzene. 3100 to 3000, overtone combinational, as I have said, 2000 to 1700, many overtone combinational differences band you are finding over there, and CC stretching vibrations, C double bond C. This is the range. Okay, so sometime somewhere range is mention is different from the other. Always 25 centimeter inverse in such kind of aromatic hydrocarbons, aliphatic hydrocarbon is appreciable, accepted, the differences. So this is benzene, you can find more than 300. These are the CH function, C double bond C, here 1400 to 1430 to 1600, 1400 to 1600. Likewise the CH, and of course these all are bending vibrations, we need not to bother about it. Now come to the oxygen containing compounds. Okay, so here we are having alcohols and phenols. As far as alcohol is concerned, I told you that alcohols show their peak OS stretching at 1600, more specifically 3700 to 3450 you take. This is the long range where they can absorb anywhere when they will have hydrogen bonding, and the nature of that peak will be very broad. What are the two different type of hydrogen bonding? Intermolecular hydrogen bonding and intramolecular hydrogen bonding. When intermolecular hydrogen bonding is there, that molecule, this is the hydrogen of this particular molecule, and this is the hydrogen of that particular molecule. This oxygen interacted with this hydrogen, and this hydrogen is no more associated with this hydrogen. Sometime it is associated with this oxygen, and sometime it associated with this oxygen. So it is just like, it is not, that's why it is called as a dynamic. This hydrogen is no more belongs to this oxygen, no more belong to that oxygen also. It is somewhere here playing between this oxygen. So because of this, charge separation is very high and broad nature of the peak that you will have for this particular molecule, okay, or OH. And here vibrational frequency, when intermolecular hydrogen bonding is there, shifted to higher wave number. Higher wave number means toward 4000. When you are having intramolecular hydrogen bonding, shifting toward lower wave number. So when you are having intramolecular hydrogen bonding, you see the hydrogen bonding within that particular molecule. This is hydroxyacetophenol orthohydroxyacetophenol. Now here in this particular case, you can find intramolecular hydrogen bonding is there. And if it is para, then you can observe the same thing for intermolecular hydrogen bonding. So para and ortho can be distinguished. One for intramolecular, you will have less vibrational frequency absorption, whereas intermolecular, more vibrational absorption frequency that you will have. Okay, so in case of alcohol, broad nature, when you will have, and I said, when you will have sharp, intense peak for OH, there are two conditions. Either one, your molecule must be there in vapor phase, and it's very difficult. Of course, there are the IR spectrophotometers, which even vapor pressure, vapor like environmental analysis, no. In that case, some vapors analysis can also be done. So that particular IRs are called as a portable IRs or some non-dispersive type of instrument. But here, when we say FTIR, here we need to either go for the pelleting or mulling. So when we do the pellet, so that time there is very much difficult possibility, so that this molecule to take in a vapor phase, we always need either in solid or liquid. So condition to get a sharp peak for the carbonyl either is should not with the hydrogen bond. That hydrogen bond when will not be there in the molecule. Either that molecule should be there in vapor phase. In vapor phase, no hydrogen bonding, or that concentration should be there less than 0.01 molar non-polar solvent, so that this molecule will be far away with each other, even though they have the capacity to form the hydrogen bond, but in between non-polar solvent, they will not allow them to form the hydrogen bonding. Anyway, so here, when you find the sharp peak at 3450 to 3500, so in that case, you can have sharp peak for OH, and that is because of the OH only. Just a minute. So this is the OH. Okay. Now phenol. In case of phenol, if you see, we know that we have learned many a time, phenoxide ion is more stable than phenol. This is OH. So this OH is absorbed in the range of what, 3550 to 3000, and most of the time phenol peak is somewhat sharp. Why? Because a phenoxide ion is there, OH is there, but before releasing this one, no, it will show sharp peak, because this results higher stable phenoxide ion. And CO stretching, of course, C and O is C and O, alcohol, here double bond CO, alcohol, single bond region, you can say CO, CO, this is CH3 suppose. So this is CO or that is CO, that is observed in single bond region. Okay, so in case of alcohol, what things you keep in mind? Any alcohol containing organic molecule, if sharp peak is there, then that must be in the non-polar, or else most of the time, or another condition I can tell you, that there is a formation of hydrogen bonding, that chances must be very much less, or no hydrogen bonding, then and then only you can have the sharp peak, like in case of intermolecular hydrogen bonding. Okay, so like, so here intramolecular hydrogen bonding that exists when toward the less wave number compared to whatever intermolecular hydrogen bonding. And now alcohol, how to identify? Two conditions, either broad nature of your peak or sharp. If sharp is there, That possibility is very less. Your compound have that potential that should not form the hydrogen bond, then and then only the sharp peak for OH is there. Otherwise, most of the time, broad nature of the peak for OH is there. That will be confirmation of presence of OH. In case of ether, here there is no other peak in ether. RCOC, here CH3 you mentioned, or C2H5, whatever you mention, but COC, this stretching, COC, single bond stretching, you will have at 1100. So ether, it's very bad technique to determine the ethers, because this is the functional group, but don't have too much possibilities, the different vibrations. Of course, CH is there, but that CH is in any case of organic compound. The only thing is that COC, this peak, if appear at in the range of 1050 to 1150, then we can say it's ether. So this is oxygen containing compound, like you see here, OHP. In case of this methanol, no, the OHP in methanol is very broad, you see, and even in 10, because charge separation is good. And then CH, aliphatic CH, it must be less than whatever 3000. So this is 3000. So always less than 3000. And here you see carbonyl vibration, single vibration in single bond region. You see, this is single bond region here, and of course this is CO. This is again single, what we can say, fingerprinting region, single bond region, intense peak at 691 and all. This is because of scissoring, twisting, and whatever it may be. Anyway, now this is ether, as I have said earlier. Ether ke case mein, that all are aliphatic. You see, these two are aliphatic. This is for methyl. Suppose this is for methylene. So methyl and methylene, these two are there. COC 1100. This is very much important. You see, intense. So this is very much important, as I have said earlier. 1050 to 1150. Okay, so this is very much important as far as your ethers are concerned. This will be much intense because charge separation. COC. This is the case. This is the way to see that particular peak in the spectrum only. Otherwise, if you interpret all this spectrum, all this peak in the spectrum, you will get confused. Even no need. The first and most important thing that you keep in mind, that no, even good books, they have also mentioned, don't interpret all the peaks which is given in the IR. Only the fingerprinting peaks which is required, which is important. Okay, now in case of amine, no need I think so, because I have explained earlier, this is primary amine, secondary amine, and tertiary amine. In case of primary amine, 2NH are there. I said this 2NH that either come toward the nitrogen, they may go away from the nitrogen, and this is called as both they are coming to nitrogen or away going from the nitrogen, symmetric stretching, but one is coming toward nitrogen and another is going asymmetric stretching. Now this stretching vibration of NH only observed here in this range 3335, but the range, and when I say it is 3250 to 3350. Why ranges I always am mention here? The reason is that it's not only the molecule. There is a solvent effect, there is a hydrogen bonding effect, there is a substituent effect, there is an electronic effect, there is a ring effect, there is a branch effect. There are many effects which also comes into the force and which decide where to absorb. Okay, similarly secondary amines, here only NH is there, this stretching vibration, but here there is a chances of bending vibration also for NH, but here there is a no NH bending appear. This is only a stretching, whereas in case of tertiary amine there is no NH peak is observed, and that's the reason NH show doublet for primary amines. Doublet means I already told you earlier, likewise doublet, sorry, better to draw here like this doublet. It may be medium sharp. By using mouse, it is somewhat difficult on this PowerPoint presentation. It will be good at camera. Anyway, so here, this kind of peak you will have for the doublet. This is kind of doublet. The terminology comes from NMR only. This is doublet. So it is because the primary, because one nitrogen associates with two hydrogens, and then NH, of course, NCS stretching, we are not talking about it. First of all, we'll talk about the secondary amine. And the same region, same range, if I find only sharp, medium peak, then that is because of secondary amine. And what about this tertiary amine? There is a no peak at all existed in this region. We conclude that this is the tertiary amine. NH peaks are also responsible, only the thing that we can find out primary, secondary, tertiary. And the supporting information we can also get NC stretching, CN stretching, so 2780 CN. Okay, then we are having NH2 scissoring, NH2 bending. Here you see I said earlier 1500, less than that all bending occurs. But here you see, you can find some exception always here. In case of amines, the scissoring and bending vibration occur in the range of 1615 to 35, whatever. So this is kind of exceptions that will help us. But again, no need to go in detail. Just to focus your concentration, or you just concentrate on the area which I told you earlier. NH, doublet, primary amine, single sharp medium peak, secondary amine, and tertiary amine. Because CH is not too much sharp, too much intense, it is moderate. But whereas amines are somewhat more intense medium type of peak in the IR spectrum. So here in case of aniline, you see exactly W shape or not. Either it is having likewise W or it may have likewise W. Okay, if you draw one more time for NH, it may happen that some peaks can shift, because that time, what vibration captured by the instrument, that will come here. Okay, so this is a primary amine, you see here. This is the peak for NH stretching primary amine. The secondary amine, you see here, only single peak. You can see here, only single peak. Yes or no? And here there is a no peak at all for tertiary amine. These all are primary amine. This is aniline, this is diethylamine, and this is triethylamine. So here NH, this NH is appearing here, and this NH is not at all available here because there is no NH at all. So CN, CN, CN. Just a bit. हा हॅलो सर, मी काय म्हणलं तुम्ही जेवण करून घ्या, मी थोडं लेट आहे लेक्चर मध्ये. ठीक आहे, हा हा मी तुम्ही जेवण करून घ्या सर, मी येतो नंतर अर्ध्या तासाने. ओके, थँक्यू. Sorry for the interruption again. Here you see, of course, I think that idea is clear. Primary amine, doublet, secondary amine, single, and tertiary amine, no hydrogens. Then come to the last point of our discussion, because I think I have taken a lot of time and I need to finish second introductory part also for Scifinder. Now here you see carbonyl group. Carbonyl group, we know carbonyl C double bond C appears there somewhere. I have already learned about this. Now it's time to talk about carbon and oxygen. And when we are having ketone, you see there are 5 different factors which affecting the carbonyl vibrational frequency, amongst which only 2 I have taken here. Otherwise it will be a long topic, it will take almost 30 minutes. I don't want to spend that much time in this thing. Now when I say the 5 different factors which affect the characteristic vibrational frequency of carbonyls, what are the different 5? So first one is the state, whether it is vapor state, whether it is liquid, or it is solid. Okay, then ring strength, where lower I have mentioned here ring strength, electronegativity effect. Okay, and then conjugations, and sometime inductive effect, mesomeric effect, and resonance effect. All these effects which actually have that shift of carbonyl from either lower or higher wave number. But ketones, when we say, and we know that when it is interacted with the IR radiation, then you see any spectrum of IR, you will have more intense, or intense generally, not medium. It is intense peak in any spectrum. So ketones, only carbonyl group is there. Of course, if I draw acetone, CH3, CO, CH3. So here you will have carbonyl. That carbonyl is observed at 1750. If only that peak is there at 1750, then you can say carbonyl, but we cannot assure, no. But at the same time, any reaction, suppose at the same time, these carbonyls are also very much important as far as the reactivity or reaction real-time monitoring is concerned. What is reaction real-time monitoring? For example, I want to do the reduction of this carbonyl into alcohol, CH3, OH, reduction, and this is CH3. So I have either used LiAlH4 or NaBH4, any reducing agent you take, LiAlH4, whatever. So that will result in OH. So my intention that reaction progresses, reaction start. So initially you will have peak at 1750. Sometime in NET examination, such kind of questions are asked. A is having the absorption range is 1715. After reaction with lithium aluminum hydride, it appear at 3300. What are your A and B? So my A is alcohol, which is carbonyl, which is responsible for 1715. Alcohol is at 3300. So when I am having the peak at for this carbonyl, so my peak is like this, from 4000 to 500. Initially, I will have that intense peak here for carbonyl at 1000. Here you take 1750. Here I am having intense peak. And at the same time, reaction progresses. When reaction not started, for here next in the machine itself, you imagine, or in instrument, that reaction is going on. You have not added now the lithium aluminum hydride. Initially your starting material is there. Now machine will give only the peak at here. Okay, here only. But when you add lithium aluminum hydride, this peak will get start reduce. After some time, again here itself, here I can draw here on the above, not this, here only it will decrease its intensity, and somewhere in 3300 you will have small peak. When you will have this decrease, that intensity increases for here oxygen OH, here again decrease, here intensity increase, here nil, here you have most intense. So what you can conclude, that real-time monitoring means we can see that ketone conversion is going on and it is converted to OH. So this peak will start disappearing and new peak start appearing. So this is also called as a real-time monitoring of the reaction. And many a time people use this kind of thing that wanted to find out the reaction dynamics and reactivity of the functional group. So this is I have explained with respect to ketone. Many carbonyl group you can take, and accordingly the this reduction in alcohol formation is there. So my intention to tell you all these things is that whenever you are having carbonyl and you are not going to discriminate between whether that carbonyl is of aldehyde, ketone or something else and all. So initially you need to know about the carbonyl only. If that carbonyl is aldehyde, I will search for the CH function again on the IR spectrum. Where that CH function observed? Again, it is observed in the CH range, but that is aliphatic, and aliphatic ko pata hai apne ko. What is that aliphatic? It is ranges from 2850 to 3000, to 3000, and this is again confuse us that whether it is of CH of your aliphatic type or CH of aldehyde. So in that case, it is always less than what 2800, like you say 2750. If in this range, you will not get any CH absorption function except aldehydes. So aldehydes are going to get absorbed. Aldehyde CH absorb at 2750, and along with that you will have 1715 or nearby 1725, 30, whatever. So previously we were confused that CO absorption is of ketone or aldehyde, but when we find the extra peak here because of CH, then we can conclude the aldehyde, or if it is not there, then we can probably say it is of ketone. Then if it is ketone, if you wanted to confirm, then you should have some more information about the bending vibrations or the single stretching vibrations of ketones also. So what is inductive effect? We know that. Here you see, this is carbon and this is oxygen, and if electron withdrawing group is there, then bond length is decreases, because oxygen, this group electron withdrawing group like nitro, it is taking electron from carbon will feel deficient, and it will now the flow of electron from oxygen to carbon and carbon to electron withdrawing group, and therefore the bond length is little bit decreased because oxygen is shifted little bit toward this carbon, and bond length is decreases means your vibrational frequency also will be decreased somewhat little bit. Previously we were expecting this somewhere exactly at 715, but it will appear at 1720, 17.5 and so on. And resonance effect, now you see here, if the this is electron donating group, then carbon oxygen will take, and this resonance means like here in between. So somewhere this carbon oxygen will be single bond or double bond, single bond or double bond. Now somewhere machine capture or instrument capture the single bond only. So where this shift in machine will, like instrument will have the vibrational frequency higher. toward the higher wave number. So bond length is decreases, again that is based on Hooke law. Decreases toward low wave number, increases higher wave number, and so on. So here again ring effect or ring strain. So ring strain is less, so value is less. Ring strain is more, value is more. Ring strain is more, value is more. What I can conclude now, as ring strain in carbonyl increases, the absorption frequency also will get increased. The vibrational frequency of carbonyl is directly proportional to the ring strain in another way, you can say. So this is what all about the ketones. Now here you see, in case of ketone, as I have said, you see most intense peak, which is looking, this is 1715, this is for 2-butanone. And CH function, of course, this CH function appears at 299, but it is always less than 3000. Here aldehydes, aldehyde ketone, comparison between aldehyde and ketone, as I have said earlier, this CH function, where it is CH function appears, you see CH function of alkyne and CH function of aldehyde, 27205, you see here. CH function of alkyne and this CH function of aldehyde. I said the alkyl 2850 to 3000. So this value ranges from this range, and this CH stretch of aldehyde actually ranges to 725. This is the way, and this carbonyl is again as usual form, but as intensity increased, there was 1715 for ketone, now 1731 for aldehyde. Same way carboxylic acid and ester also. Same way carboxylic and ester, where OH. Again carboxylic acid discussion is too long. Carboxylate ion is there. Then what you can say, the carboxylic acid is always existing except vapor phase in dimer case. All carboxylic acid, most of the carboxylic acid in general, they are exist as a dimer except in vapor phase. So dimer means we know there again hydrogen bondings comes into the picture, and then OH stretching peak you can find, but this is a sharp as compared to what your OH. This is sharp as compared to what your OH. CO stretching again a sharp exact as 1700, and CO single bond stretching 1240. Similarly for esters. Now for ester, this is the advantage. C single bond O stretching, aromatic and aliphatic. This is again sharp peak that I will show you. This is again sharp peak. You see CO. This is ester. This is CO. This is CO. Sharper because single bond sharp. This is charge separation is good, and C double bond O you can find again as usual it is sharp 1752. It is exactly as 1700 this acetic acid ke liye, and this is what we can keep in mind. CO carbonyl stretching 1715, aromatic carbonyl stretching 1730-05. Now when we say all these things, acetic acid and this acetyl, just look to the structure and find what are the different possible vibrations are there, and just try to predict what the knowledge that you are having earlier. Amides are also here NH, and no NH. Primary amide, secondary amide, tertiary. Values again you can find it out. The same thing is there, not more than that. And anhydride, which is a peculiar case where you can find 2 carbonyl. Anhydride, where you can find 2 carbonyl. What that 2 carbonyl? The 2 carbonyl of unequal intensity. Unequal intensity means one is equal and another one is less equal. Why is it so? Because this is in resonance. Because we know that here it is coming, one is OH and then one is remain as carbonyl. Again, this will come back, one is OH and one other. So OH, whatever it will be there, that will appearing as here. Sometimes the less charge separation will be here, and that will appear as a here, less peak. So this is how the peak for carbonyl, 2 carbonyl you are having here, 2 carbonyl over here. Similarly for benzamide, same doublet appear because of NH2. This is just like what amine, but except to 650 means that is 6054, 1651. Sorry. So in this way you can discriminate, you can distinguish, and you can just make a chart and try to find out the correlation between it. And what I have given the group frequencies, that will help you to interpret that whether the given structure is because of or the given vibration is because of the that particular vibration, stretching, bending, and all. Don't interpret rest of the peaks in IR that will leads you in misleading. Okay, so what are the important vibrational frequencies in the IR spectroscopy that you are having that information, values, the phenomenon, the background, and all these things you compile very well in your mind. I will suggest you one or two books, and you can develop your understanding far better in IR spectroscopy. So those who are a beginner in the research, if they have the IR spectrum in their hand, they can conclude that this is the functional group previously we had, and now after transformation, this functional group addition you say, interconversion you say, elimination you say, or transformation, all these things can be done on it. So thank you very much for attending this topic. So any doubt, any difficulty with respect to what IR spectroscopy, you may ask, or should I go for the next topic?
Sir, there were no questions in the chat box, so I think you may continue with your next topic. Or if they have some questions, we ask them to drop in the chat box.
Okay, fine. So
Is it fine, sir?
yeah, fine, no issue. It's always
Yeah.
fine for me. I'm going as per the students' interest and all. Here you see the next topic is introduction to Scifinder and CAS. What is mean by Scifinder first of all? So again, this is paid services. Whatever Google you are searching anything, any question paper, or sorry, any research paper, anything else, or any information, Google show you only 8% information. What is free of cost? What you people are getting? 92% information is not available or accessible for the normal common layman people. So now how to access this particular hidden 92% information? It's not only about the research, it's about the business and other things are also. We are, what free we are getting is only 8%, 92% again hidden. So to take out that information of interest, okay, so these are the some databases. We need to pay some amount, then and then only they will give you the access, otherwise not. Okay, so Scifinder is a database. This is very much important. Database kiska hai? This is a database of chemical abstract services, CAS, chemical abstract services. Means it's a database of all the chemicals and the research articles you published in one platform. So for example, yesterday, you people enjoy a very interesting talk of one of my senior, Dr. Atul Nagpure sir. He was just senior to me, and he told you that how you can publish your work. Initially, you need to write your manuscript in a proper format. Of course, your heading, title, you can say, then your name, affiliation, abstract, introduction, result and discussion, then conclusion, acknowledgement, and references in a particular format. That template is available on each journal. Once you fill all these things, you need to write all these things. Once you fill with that particular paper that called as a scientific community manuscript, that is called as a manuscript. Now it is ready to communicate with any journal. Now imagine there are not in thousand but in lakhs of journal for only chemistry are available. I'm telling you, I'm repeating again, it's not in thousand, it's lakhs of journals are available around the globe. Now among these journals, which journal look fit for my research work? That I should know first of all. So there are certain publishing house, publishing agencies, or you can say publishing portals. ACS first of all, American Chemical Society, a publishing house which is situated itself here in America, Columbia, Ohio. Then we are having elsewhere a publishing house again. Then we are again having Ville, German based. This is UK based, German based, American based. Then beside this, Bentham is there. Some Arabic or the Islamic world countries, and there are other portal also. Even India also having some kind of bits and all things. So each portal will have this their own journal. I'm telling you, thousands of journal only for ACS. Thousands of journals are there for elsewhere. Thousands of journal for Ville. Thousands of journals are there for Bentham, and many thousands becomes a lakhs, more than that. So you see, amongst this, which I need to select. Suppose I am doing work in organic chemistry, and I know some of the journals like tetrahedron, Then organic letters, Journal of Organic Chemistry, Journal of Green Chemistry, simply Journal of Organic Synthesis itself, and many journals you can see. So I have selected. So that is again Journal of Organic Chemistry, JOC is there here for ACS. Here tetrahedron letter for elsewhere. Ville, you can say Asian Journal of Organic Chemistry. For Bentham, Current Green Chemistry, and many. There's just names I have given. Many things are there. Now I have communicated with this or that. It is published here in elsewhere. But before writing anything or before research, what we need to do, literature survey. This is very much important. Why literature survey is important? The reason behind it is that whatever we are doing in the laboratory is already done by the people, or that's something new, which is I am doing in my laboratory. So parallel research is also going on in on this particular globe. Like whatever we are doing in the laboratory, somewhere in any country, in one corner of the country, people are doing the same thing. And the thing is that who is publishing first? That is very much important. So how I will get to know that people have done already work on this particular field or not? There should be a database, so that in that database, all people publishing in any journal, but that database find all this. So all these lakhs of journals published work you can find here in this Scifinder in one stroke. Earlier in 1980 before or 1990, whenever that Scifinder or some kind of databases, online e-databases have not generated, no, people used to go to the library that per certain volumes, issues of a particular journal they were coming, and whether our work is or related work is published or not, every week or every monthly or every yearly journals are there that we need to go, we need to see that whether work is published or not, and all around what our work is published, nearby that work is there or not. Likewise, we need to take it out by manual way. But here in one stroke in Scifinder, you will get to know how many people in the world have worked on that particular topic, what is new, in which journal they have published. Everything you will get to know here itself on the Scifinder. Just you need one login and password. As I have said, this is a paid service. Very few institute they have the access, because as it required to pay in crores. I think Mumbai University has paid 3 crores rupees to get access for 3 years or 1 year, I think. Now this is CAS sorry, it's not a what in for the professor we are having this CAS, no, career advancement scheme. It is not, is chemical abstract services. So there in that database you will able to see only abstract, and they will give you a link. On that particular link, if you click, that will redirect to your journal. That journal, that paper you can download from this. If you are having access, then and then only you can download. Which access? Again, you need to pay differently for Scifinder to give all this information in one portal. But suppose that paper is published in JOC, for example, and University of Mumbai don't have access to JOC because separate money needs to pay to get access for JOC. Then only they will give access for full paper. Otherwise, you will be happy with abstract only. That abstract either you will get on Scifinder or on JOC. So you see, this is the kind of business that people have made. And some of the free literature databases are also there. You need to take just a DOI, digital object identifier number, and need to paste in Scifinder, sorry, Sci-Hub. So Sci-Hub is a very famous researcher, those who are actually from the Russia. That lady have created her own database. Whatever the papers she is getting from the globe, she is unofficially adding in her own database, and by looking to the digital object identifier, she is providing that complete paper free of cost. This is a very good thing that she is doing. Okay, anyway, so let us start with the Scifinder CAS online real demo. So I will log in, whatever the user ID and password is there with me. I am logging with that thing, and you only tell me that which structure I should have to draw and what type of information I need to find it out. Okay, so you see, I can say aspirin. Aspirin is orthoacetyl salicylic acid. So how many people have synthesized aspirin by using what method, which are the new method, and recently how many people they have worked. that all filters I am having itself in built-in Scifinder. So I hope the Scifinder is nothing but the database, and this is associated with what American Chemical Society. As I have said elsewhere, there is one different database maintained by elsewhere called as Reaxis. Reaxis. This is again a database which is maintained by the UK people or UK community, scientific community, chemical scientific community. So either you have the access with Reaxis or it may with Scifinder, one and the same thing. But the thing is that Scifinder having some advantages over what your Reaxis. Reaxis taking the published work and update, means suppose today you have published any work, and to get that work in Reaxis database takes almost 6 months. But this is not a case with Scifinder. Once your issue becomes online or paper become online, that day onward you will have that paper in Scifinder itself. So let us start with the real demo of your Scifinder. So this is Scifinder login. I'm trying to log in with my username password. Yes, so this is the home page of Scifinder. You see, this is Scifinder, and here you are having different tabs. Search topic, anything, even botany thing, biochemistry thing, zoological thing, all things that I can search here. If you wanted to see synthesis of orthoacetyl salicylic acid or aspirin, so whatever information related to that words, you will have many hits and many articles published based on this one you will have here. Okay, you can search by any author name. If you are searching for any author who is doing work in the chemical sciences, his whole database you can have find here itself. Okay, then company name. Of course, we are not only the academic people doing this research, all industries, specifically fine chemical laboratories, even the crude petroleum industries, they are doing some chemical research there. Document identifier means DOI number. Earlier I said every paper we have its own DOI number, digital object identifier, that we have here. Of course, journal, you need to find out journal name, volume, issue, starting page, so you will have perfect that only information. Patents are also you are having over here, and you can find this by using different tabs. As you can search from here research, but most of the time I am searching by using this window, reaction window. So reaction structure, when I click on the reaction structure, I get some ChemDraw like window, and I said earlier I'm trying to draw orthoacetyl salicylic acid, for example aspirin. Okay, so here, or paracetamol, simply very much common you say. This is OH. Here from short OH I am taking. This is OH, and here, sorry, carbon. Then here C, N. If I am not wrong, I am correct with the orthoacetyl salicylic acid. It's NH. Here oxygen you will have, and here you will have CH3. Yummy. Okay, so this is a paracetamol. This should be CH3. Okay, CH3 Me. And now whether this structure I need to search as your reagent, starting material, or product, that you need to decide. I am going to start for the product. So if product is there, means after the arrow, that will search only for the product. You see product word automatically comes. If I don't want to search as a product, then I want to search as a reactant, then I will go to add arrow just front of the structure, so that will become reactant. Okay, automatically. So I am searching here for as a product, and I am just doing okay and searching in the database of Scifinder. Scifinder is searching now. and whatever data is there with us is like retrieving data. You see 4,138 reactions are available. So people took NH2OH and this fragment becomes orthoacetyl salicylic acid. You see many, and if you want documents working, you see this is an environmental benign catalyst free CIN bond cleavage. This is all these things you will get to know here. Many get references, for example. You see, this is the patent 958 ho gaya, and then means I am telling many filters we are having here. We need to just put that filters here. You see, analyzed by CAS registry, analyzed by company organization, analyzed by database. Just wait. हा हॅलो सर, मी लेक्चर मध्ये मी नंतर फोन करू का तुम्हाला? हा yes. So here database, journal name, language, publication year. I can even arrange them in a proper direction, whether it is journal name ke hisab se, then you can have the publication year, supplementary, all these things. Now I want get reaction. I am trying to get the reactions. Again, I will come back to that particular window. Okay, that window comes here. Overview I am taking. You see, overview means this is view of reaction link. This is the things that people have done. The condition use aspirin final product we need. Okay, but here I'll come back here again. Sending in database, sent in database, searching. Okay, so when I am having here this paracetamol, I can see overview. This is published in 2021, last year, in the 41 issue or maybe volume, and this is the page number and year 21. Okay, which journal? European Journal of Organic Chemistry. And environmental benign catalyst free CNC bond cleavage formation, primary, secondary, tertiary unactive amides. So these are the amides, of course. What are the condition in general? And if you want full paper, then how I can have the access for complete paper? You see here, other sources are there. Just click on other sources. Automatically, it will be redirected to that particular journal link. You should have strong network connection. It will take time, of course, because much more database is stored. So full CAS full registry. This is the DOI number, digital object identifier. Click here. Then automatically will go to that particular paper, EJOC, European Journal of Organic Chemistry. This is the paper you see. You can find. These are the people, Vishal Kumar and all to this, whatever it may be, Carbomath something. So here you see the complete paper. How to download complete paper then? If University of Mumbai suppose have access, then we can download PDF directly from here. If it is not, no access. They will say no access. Here you see. Get access to the full version of this article by logging with the different institute, because University of Mumbai don't have access. Either you can go with the purchase. You see $12 means almost more than like you say 1200 and all. So we don't have that much money. So if suppose this is the DOI number, if it is not recently, if it is added by the Sci-Hub, means that lady of Russian lady, so you will get free of cost. If she has not added because she is not getting from any source, so that will be not there. If it is there, then you can go just by clicking over and there, and you will be with that particular paper. So what Sci-Hub is saying, sorry, Sci-Hub has not included this article yet, means it is recently published. That's the reason. If it is 2 years before or 1 year before, that you may give from the Scifinder, or you need to wait to get this one, or else whatever institute that EJOC access is there, you just copy this DOI, come to your mail, paste here, add to your friend where that whatever the information is available with us, add, please provide this thing and send. That friend will send you the PDF copy. What he need to do? Just he need to click on the PDF, automatically will download. For example, if suppose any other paper which is downloadable here, we can say, or otherwise just like PDF, we can download. Another, Journal of American Chemical Society, and again 2018 it is published. Journal of American Chemical Society, JACS, 140 volume, 15 issue, page number this. Again the same thing. You click on other sources, again you will get DOI redirected to the main journal, and you can download. What does it mean? This Scifinder is not only showing information from the European Journal of Organic Chemistry, but it is also providing information about this patent pack. This is Journal of Porous Materials, then Nature Communication. You see here, Nature Communication. So whatever work related to that molecule or related to that material, everything we are here. We need to just see 4133. This is 83 page. I am looking only for one. This is the one page. Then I will go to next, second page. It will go to the second page, second of 183. Likewise, all we need to do. Sometimes similarity, if I omit, then that 83 page become less. So similarity means sorted by accession number, experimental procedure, methods, now number of steps, product yield, publication year. This will get sorted according to their filter. Grouping, document transformation, that grouping also you can do. Reagent, अभी अपने को इतना सारा देखना है कौन से reagent यूज किए नहीं है, हम catalyst से यूज कर सकते हैं, catalyst से सर्च कर सकते हैं. Then how we can see the catalyst? Show more. You see, and 6 pages are there. I directly export on my desktop as a PDF. Export. So all PDF will download, all 6 pages will download here. And you see, these are the catalyst these people use for the transformation of these two spaces into that, which here reaction not containing information for the analysis. That much reactions, 2407 reaction. Don't know which catalyst they have used, but you see 385 reactions they use palladium, some of them 172 use nickel, 169 use NaOH, 145 likewise. You see 6 pages I have said all these things. So you don't go systematically. If you are interested by doing this reaction by DAPCO, so control F and find DAPCO whether it is available. Yes, only one reaction somebody has done with the DAPCO, and you find out which is on this one and find out who has work and how that person has done. Then here only show more. Then you need to go for the DAPCO whenever it is one reaction only, whatever DAPCO. और अभी देखने के लिए टाइम लगेगा. For example, iridium, how many people are doing? Apply. So only 2 paper that will show. The database only show 2 papers. You see here, out of this one, what I need to give command? I need to give command just which is hiding to the talking. Just wait here. Keep analysis. Once I click on the clip analysis, only 2 hints that database will provide. This is 2 hints now. 1 hint and second hint. Overview. You will have all the process, organic process research and development by Sowana Oshinari. This published, and you can go to the other link, DOI again, go to the journal, download PDF. So this is the way. So it's not only showing the information of the reaction, whatever the molecule that you wish to synthesize. For example, on one molecule that I am working, you see, there is something what? Phenacyl bromide. I will show phenacyl bromide, then pH NCS. Here nitrogen, carbon and sulfur. NCS, phenyl isothiocyanate and acetyl acetone. Anything you can, hydrazine I can take it. Take hydrazine. Okay. NH2. So it is this is phenyl hydrazine you take, and I wanted to do the reaction. Okay, for this. So whether the reactions people have done or not, you will get to know from the Scifinder. You see, retrieving data, only 8 reactions have done by the people, you see. Okay, this is what near about, not exactly. So what does it mean? That if you wanted to do some kind of work, whether that work is done by someone, some other people, what reagents they use, what catalyst they use, and what not, you will get to know everything. Even extra function for that Scifinder is there, but I'm not too much familiar with that, is Marpush. This is Marpush, which is giving planning. For example, natural product is there, recently isolated somewhere, someone from the natural sources, and what he is or she is doing now, the synthesis in the laboratory. So Marpush is a kind of data, instead you can say artificial intelligence, which is providing us the systematic steps for the synthesis of final product. Means it is doing retroanalytical synthesis by artificial intelligence, and it is giving steps that you do these steps, you will get that, and you do that one. Likewise, many steps it is giving, because we know that natural product synthesis takes very much steps, like cholesterol, or we know more than 17 steps are involved for the synthesis of cholesterol. So this Marpush will give you a strategy that these are the chemicals you people require, and this is how you can do. I'm not too much familiar, that's why I'm not telling you, but this is the real thing. I will learn. Of course, no need to, it's not too much difficult to learn. Just go to the YouTube, you write something that how to use Marpush in Scifinder. 30 minutes, 20 minutes, 5 minutes videos are available. You read and do accordingly, you will get to know. One more important thing I wanted to show you here is a research topic. I wanted to find out the information about the recently anything you can say, for example, aspirin, synthesis of aspirin. Synthesis of aspirin using acid, using any catalyst name, using iron as a catalyst. Iron as a catalyst. So whether people have done by using iron catalyst the aspirin or not, that we can just enter these words, be very specific with the words. It will search for synthesis, it will search for aspirin, and it will search for iron as a catalyst. So here you see. Only one reference they have found that all 3 words included. And synthesis of aspirin using iron as a catalyst, 8 references. What does it mean? 8 references they found in the paper, they found in heading. You see here, one reference was found containing all the concept of synthesis closely associated with one another. And 8 references were found where all the concept of synthesis were found anywhere in the reference. Anywhere in the reference means anywhere in the paper. Anywhere, like it may be reference, it may be conclusion, it may be result and discussion, it may be your heading, it may be your abstract. But this is as a whole incomplete paper. Now 24 references which only have synthesis and aspirin using iron. Then synthesis, iron, likewise. So you can find at the last, sorry, by mistakenly I have clicked on that one. Okay, I'll come back. Now you see 33 lakh 10,969 references found which have the word catalyst. Iron and aspirin have 164. Now I wanted to see only 1, 8, 24, 47, or only this 164. You can just click whenever, whatever information you want that much, you can click over here. But this database not search more than what 10,000. It will execute 10,000. Then there is a limitation for us, because after 10,000 word, that is hided. Means hided means it is not showing to us. So what the next strategy we need to apply? We need to modify these words so that minimum references you will have for that particular search. Again, I have not changed anything, same thing will remain, and I wanted to find this and that. So get references. So I'm getting 9 references for this only. So 8 references, and I'm searching here from get reactions. no reactions are available. Okay, so I think they are having this much, I think, patents only. Here you see sources you find environmental science and technology 2155. This is this thing, so you can click over here. Okay, then again you go to the other sources. Sorry, other sources. So other sources mean that paper you can download. As I have said earlier, no, same strategy you need to follow. DOI number, and that DOI number that will automatically takes you in that journal. If you have accessibility, you can download in PDF, or else you can go to the, as I have said earlier, which Sci-Hub, if the access is available. I think here access is not available, or it is available. I need to go through the institutional login, and I don't have right now that institutional login. But anyway, that where DOI number, this is the DOI number. You need to just copy, and if it is available in Sci-Hub, you will get, or if it is not, you need to send the same mail to your friends, those who are having the access. That friends you will get in future, those who will work in the National Institute and all. I hope that this is okay. And I said that from my side, I have completed over, but any doubt, any difficulty with respect to this and earlier topic, you may ask the question. Yes, am I audible?
Yes, sir. Yes.
Yes.
Sir, 2 to 3 questions are there in the chat box.
Yes, yes.
I read it one by one.
Yes.
Sir, Bhanu want to ask that, sir, please tell about FTIR, and please tell us why electric field is perpendicular to magnetic field in electromagnetic radiation.
You see, this is a very, very basic question, and the better understanding you will get to know in 12th class itself. Okay, why they are perpendicular to each other, why they are not in the parallel and all that you already learned in physics in 11 to 12 standard. The thing is that we know that any electromagnetic radiation which is having the electric field and magnetic field perpendicular with respect to each other, and there are thumbs rule which is again signifies that all discussion is a physics background. What is FTIR? FTIR means it's a Fourier transformation processes. Now again, it is a very long topic. Fourier transformation is what? We are getting the spectrum in time domain. That after applying this Fourier transformation, we'll get to know the spectrum in the frequency domain spectrum. Now when we comes to the Fourier transformation, previously the people use manually, like I am having 4000 to 500 centimeter inverse, that long range. With respect to time, I am passing the radiation. For example, 5 centimeter inverse, that command I have given to the instrument. First of all, 5 centimeter, then 5052, 510, 5152, 520, 525 to 30, and so on up to 4000. That will take a lot of time. And whether after interacting with the sample, if absorption is there, peak is arises. If absorption is not there, null and void 0 dash. But what we are doing in Fourier transformation, it is internally calibrated, sensitivity is high and all. This is a kind of algorithm. It is actually, I can say, time domain to frequency domain we can convert by taking k cos of 2 pi nu 1t. This is what pi means. Pi means point of circumference, what we use for that particular wave. Nu 1, what does this mean by that? Nu 1 is a frequency which I have passed earlier for 5 centimeter inverse. T means with respect to time, plus k cos of, k is a constant, k cos of 2 pi nu 2t. What is 2 nu 2 now? That nu 2 is another frequency that I have passes from 501 to 502. And what is nu? Again, same constant formula is there, but nu 3, nu 4, and so on. But for 1 or 2 frequency, this is very simple. तरी 15-20 मिनिटं लागेल. तुम्ही निघत आहे का? जेवतो नंतर येतो 15 मिनिटं. Okay, sorry for the interruption again. Now here you see, this is the way the time domains. What does it mean? That all radiation we are passed at one time, okay, on the sample. And as just wait, sir. ये तो ना अरे आ रहा हूँ ना मैं, दरवाजा बंद कर दो। अरे दरवाजा बंद कर दो प्लीज। सुन रहे हो, मेरे को पता नहीं म्यूट कैसे करना फिलहाल के लिए। प्लीज आई एम रिक्वेस्टिंग यू प्लीज, थैंक यू। So sorry, it's quite late. No, that's the reason my colleagues are calling me. Anyway, so here I will go. No issue. Here, the time domain spectroscopy into frequency domain spectroscopy. Here, if I go the discussion, it will take a lot of time. That's the reason I'm very much concise. Here, just wait. Okay. Yes. So for example, I'm passing one wave. After interaction with sample, I will have a peak. Okay, after interaction with the sample, and if this is new one, there you will have at new one. If I am using different wave with a different frequency, of course I will have at another case. This is new two, so here new one, new two, both different peaks I am having. Now what happen if I use both this one at one time? I will have two peaks in one spectrum. This is very simple for two frequencies, just like I have said 5002, 501. This is for 5012, 500 to 505. Sorry, here 5052, 510. And now what about then when I am having third wave, fourth wave, complication will increase or not? Yes, and during this wave they will communicate with each other. No, they are having two different types of constructive and destructive interferences. And when they will have constructive interference, one, okay, so constructive interference means the intensity of the particular peak will get increased and one beat is arises. Okay, this is called as a beat stream. Now this what you are getting everything in frequency domain. This is all associated in time domain. Power of radiant power with respect to time and power of radiant with respect to frequency. This is frequency, this is with respect to time. And time domain spectroscopy comes under whatever Fourier transformation, where we are not able to identify or interpret this time domain spectroscopy. Once we applied FT, this is all computer program algorithm. I have given the formula that how to convert this time domain spectroscopy in frequency domain. So time domain spectroscopy with respect to power of radiation is equal to K cos of 2 pi nu 1t plus this. When I say this equation, K cos of 2 pi nu 1t, constant, cos is angle, then 2 pi again constant value, nu 1 is what I have used the frequency with respect to time. So this frequency only will get changed. This is very much simple calculation for one or two waves. But what happens when I am having many peaks, many frequencies, dash, 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 the scene will be very much complicated and you will have such kind of peak. This is a FT, and when we allow the convert to FT, we'll get to know the spectrum which we can interpret on our own. So this is FT spectroscopic technique. In short, whatever complicated things are there with us, that will simplify by the FT instrument. And again, when you go in detail, Michelson interferometer is there. That Michelson interferometer inbuilt with the fixed mirror and then movable mirror, laser is standard, source of radiation, and many more things. It's not a topic that we can explain in a 5 minutes or 2. Okay, I hope those who are really interested now, they can read Scoop. I'm writing here. Here I can write principles of instrumental analysis by Scoop. And what earlier I have said about the IR, no, that you can go two books I'm trying to mention here. One is very good for this one, IR Spectroscopy by Barbara Stewart. Okay, so this book will help you to understand what we have learned in this case, applications of IR in organic analysis or organic substances. So next question, madam.
Sir, no more questions are there. I like all the participants like your presentation and the way of presentation. Most of the question, most of the thing is I found in the chat box is the nice presentation and nice explanation, sir. So thank you so much, sir, for your descriptive explanation of the IR spectroscopy regarding frequencies of functional groups. You explain all the things very well, sir. Actually, I am not from the chemical background or chemistry background, but I got all the concepts which you taught us during this time. So thank you so much, sir. And you tell us about the Scifinder and the all the researchers and the upcoming researchers. They all know about the Sci Hub. It is a well known thing for them now from today onwards, and they will get the benefit of all these things. And thank you so much. Now I request
so much.
Mr. Nilesh Zada to propose the vote of thanks. Over to you, sir, Mr. Nilesh Zada. Zada, sir?
Thank you, madam. Am I audible?
Yes, sir, you're audible.
Okay. Good afternoon, one and all. I would like to thank Dr. Bhushan Popatkar, sir, from bottom of my heart for giving his valuable time and delivering such a wonderful motivational lecture on IR spectroscopy in connection with characteristic vibrational frequencies of functional group and Scifinder and CAS. Truly, sir, all the participants surely got an idea about IR spectroscopy and Scifinder and CAS. Okay. I would like to also thank Dr. Gandhare, sir, for a nice introduction of guest speaker. Dr. Mishra, madam, for comparing the session. Mr. More, sir, Dr. Jivani, sir, for their technical support. Lastly, I would like to thank all the participants for participating and listening carefully with a great enthusiasm. With the permission of organizing committee, I would like to conclude here that today's session is over. We will meet tomorrow with our new guest speaker. Take care. Thank you, all of you.
Thank you so much, sir. I must have to thank to one of my respected sir, Dr. Nilesh Gandhare, sir, for giving me this opportunity to share a little bit knowledge about the IR spectroscopy and Scifinder. Thank you so much. Thank you, Nilesh, sir.
Thank you, sir.
Thanks. Thank you, sir, for
Thank you,
accepting
sir.
our invitation.
Thank you, sir.
Thank you, sir.
More, sir?
I want to tell all the
Yes, sir.
participants that sir have just mentioned that they will share the PPT with us, and we will share you on the WhatsApp group definitely.
Yes. I'm just sharing.
Thank
this
you, sir.
now.
Thank you, sir.
Thank you so much.
Thank you, sir. Good
May I
day.
leave now?
Yes, sir. Yes,
Thank you, sir. Thank you. Okay, bye bye.
More, sir?
Yes,
Please
sir.
end the session, sir.
Okay, sir.